Hi. So in this video, we're going to introduce the idea of integration by parts, which is a new method of integrating functions, which involves the product rule for derivatives. The idea behind integration by parts is that we know the product rule for derivatives means that if you had the product of two functions, u times v, and you find the derivative, it would be the derivative of the first function times the second plus the derivative of the second function times the first one. We're familiar with the product rule for derivatives. So if you're familiar with that, what we want to do now is take antiderivatives or integrals on each of these terms. And the cool thing about doing that is that on this term on the left, I'm taking the antiderivative of the derivative of product. So that means that this cancels out, and I really just get uv. On this side, I have the antiderivative of u prime v. Sorry, I'm going to change colors. Plus the antiderivative of uv prime. I'm using the word antiderivative for integral interchangeably. So this is basically the rule for integration by parts, only that we're going to have it solved for this term in the middle. So if I solve for that term, integration by parts looks like the antiderivative or integral of u prime v is uv minus the integral of uv prime. So if you forget the rule for integration by parts, it's not hard to come up with it. It's just the rule for the product of the derivative, or the derivative of product, and solve for one of the terms, and you get it from there. So this is how we write it down. The integration by parts formula is u dv is the integral of u dv is u times v minus v du. Now, how do we use this? Why is this useful? Well, because sometimes you're going to integrate functions, you're going to be asked to integrate functions that are products of stuff like x cosine x. And an example like this I'm going to do in a few minutes, you're not going to find a simple function that works. But we're going to identify one of them is going to be my u, my other one's going to be my dv. So doing this, you're going to break it up and write it like the right side, which this part is going to be involving integrating the cosine part, but I can do that. And for this one, I'm going to have v du. So I'm going to find the derivative of the first function. So that what is up here. So I'm going to do that in an example in a minute. My first example I'm going to do is this one. So x squared natural log of x. So on this example, again, this is a product where I don't identify a simple function whose derivative would have been a squared times natural log of x. So I know that my integration by parts rule, I'm going to write it up here, said if you identify this like a u dv, you're going to have u v minus v du. After a while, you memorize this. So of my two functions, x squared and natural log of x, one of them is going to become u, the other one we're going to identify it like a dv. Which one is which? Well, in this case, if I chose ln x like dv, I would be into trouble because to find who is v, I would need to find the antiderivative, and I do not know how to find an antiderivative of natural log of x. In fact, that's going to be my next example. So in this example, we're going to use u to be natural log of x, because I do know how to differentiate natural log of x. So my dv will be x squared. So I do know how to anti-differentiate x squared, or integrate. So now du is going to be 1 over x dx, and v would be x cubed over 3. So once we have these pieces, I can put this together and say, well, why don't I color code these guys if you want? So my V parts are going to be green. Okay, and I'm going to do over here, so I'm going to write over here. I'm going to use white for the neutral color. So the integral of x squared ln x dx would be u times v, so I'm going to multiply u and v. So I'm going to multiply ln x times x cubed over 3. And then I'm going to subtract the integral of v du. So v is x cubed over 3 du, is 1 over x dx. Okay, so I'm doing this part, just following the formula. So this simplifies a little bit. I'm going to forget the colors now and do it all white. So here I get x cubed over 3 natural log of x minus, I can take the third outside, and x cubed divided by x is x squared. So that's the integral I need to solve, which is a lot easier than the original one. So I have x cubed over 3 natural log of x minus, I'm going to integrate x squared, so I get x cubed over 3. With this 3 that's over here, I get x cubed over 9 plus a constant. So this would be my answer for the integral of x squared natural log of x. Now the good thing, of course, of doing integration is that we can always check our work by finding the derivative. So let's check our work. Let's check that this actually works. So I'm going to check here. I'm going to find the derivative of x cubed over 3 natural log of x minus x cubed over 9. I don't care about the constant. I know the derivative of that part is 0. So now in the first part, I have a product rule. So the derivative of x cubed over 3 becomes 3x squared over 3 times the natural log of x, and then do the product rule. So now it's going to be x cubed over 3 times the derivative of natural log of x, which is 1 over x. And over here, I'm going to find the derivative of x cubed, so it becomes 3x squared over 9. So see what happened. In this part, I get x squared natural log of x. This is really 1/3 of x squared, but this is also 1/3 of x squared with a negative. So they cancel, and this is my answer, which is what I wanted. So this did work fine for my derivative. Okay, a second example. I said I was going to do the natural log of x. So we don't know a function whose derivative is a natural log of x. And this is where integration by parts comes in very handy. Now I have to use it in a clever way because the integration by parts rule says that the integral of u dv is uv minus integral of v du, and I don't really have two functions here as a product, unless we think that my u is the natural log of x and the dx is my v. Right. So if I'm going to do that, because that's the only way I can break this up. So if I do u is the natural log of x and dv is dx, then my du is 1 over x dx, and my v is just x. Right, the derivative of x would be 1 times dx. So if I follow now my integration by parts rule, I'm saying the integral of natural log of x dx is u times v, so it's going to be natural log of x times v. So I'm going to be careful here with the parentheses to be times v, times v, which is an x. It looks weird if you write natural log of x times x, so I'm going to rewrite it like x times natural log of x in a minute. And then minus the integral of v du, And when I multiply v du, I'm going to write it down, but I have v, which is an x, and du, which is 1 over x dx. So this becomes, I'm going to go back to white, x natural log of x minus the integral of dx. So this becomes x natural log of x minus x, plus a constant, of course. So this would be my answer. And again, we can check and get some space. And now we know who would be, oops, what did I do? I didn't finish moving it. Try that again. Okay, so now let's check. So to check, I'm going to find the derivative of x natural log of x minus x. Again, I don't care about the constant. The derivative of the constant is 0. So I have a product rule here. So it's going to be derivative of x, which is 1, times natural log of x, then plus x times the derivative of natural log of x, which is 1 over x. Now minus the derivative of this part, which is just a 1. Now when I multiply x times 1 over x, I get a 1. So minus 1 is 0, and I just get natural log of x, as we wanted. So in all these examples, I'm assuming that x is not 0, to clarify. So all these multiplications that we did here make sense only if x is not 0 and defined. So to assume that is happening. Okay, one last example for this first video of right parts. So I'm going to do x times cosine x. So it's going to be common to have a product, to use integration by parts when we have a trig function multiplied by a polynomial. So if I have x squared or x cubed times cosine or times sine, this is going to be a technique that works. Now, who do I pick for u and who do I pick for dv? Remember, the integral of u dv equals uv minus integral of v du. And I need to pick one of my functions, x or cosine x is my u, the other one is my dv. Does it matter? Well, think of two things. Whoever I choose for u, I'm going to differentiate. And whoever I choose for dv, I'm going to anti-differentiate or integrate. So if I choose the u to be cosine x, its derivative is going to go to be sine. And if I did that, then my x would have been my dv, and when I integrate, I have x squared over 2. And when I integrate the second part over here, my new integral is going to be a product of these two guys, which is going to be x squared times sine. So it got more complicated. So one rule that we kind of follow when we do these is if you have a polynomial times a function that is not a polynomial, like a trig function or exponential function, you choose a polynomial function to be your u, because when you differentiate, it's going to decrease by a power. So if this was x squared, the derivative would be 2x. So it simplifies. In my example, it's just x, so this is just dx. So it disappears once you take the derivative. For the dv part, it's going to alternate between cosine and sine, but that's not a problem. The derivative, it's cosine, so the function was sine of x. Okay, so now I have the parts written down. It's right down. So my integral of x cosine x dx would be u times v. So I'm not going to use the colors anymore. So it's x times sine of x minus the integral of the two things we calculated of v du, sine of x dx. Okay, so this becomes x sine of x minus the integral of sine is negative cosine, so this is a plus, right? Because the derivative of cosine is negative sine, and I have that negative on top of it already. Sorry, in the top line. So this would be my answer, and as we've been doing, let's check. So if I check, I'll be finding the derivative of x sine of x plus cosine x. I need the constant, and that would be, I have a product rule here. The derivative of x is 1 times sine of x plus derivative of x, which is, sorry, derivative of cosine, which is a sine, which is cosine, so x cosine x. And now derivative of cosine is negative sine of x. So these terms cancel, and I get x cosine x as I wanted. Okay, so this is how integration by parts works, and a few examples.